All right, so good. Start the recording. All right, so let's start with 102. And it says 102 lab about page 54. I'll write that down. And then let me switch over, to the lab manual. Give me a second. I'm going to have to find that lab manual. Let's see, that would be in the 102 folder. And must be in this subfolder here. Physics, lab manual, here we go. Okay, and then 54. All right, 52, 53, 54. Oh, you know what? I think I know the question. I got a lot of these by email. Are you asking about these? Let's see, 1, 2, 3, 4. The first 4 questions that are related to the tension. I bet that's your questions. Scott says he'll be right back. What do you conclude about the? What do you conclude is the math and part 2? All right. So I think what you mean, if I'm understanding the math, 1, 2, 3, these first 4 questions. Let me share my screen here so I can show you some numbers. But this is the pattern that I hope you see in that lab. Let's see, this was the standing waves lab. Give me a second here to get my camera going. Okay, so the standing waves lab for 102, I'll just put on the top here of my page. And then the numbers you see, and too bad the questions aren't numbered, but I'm going to just put number 1, number 2, number 3, number 4, and number 5. So these first 5 questions, which, and maybe that's your thing. It says, what do you conclude about the mathematical relationship? So I guess that's number 6. 1, 2, 3, 4. No, that's 5. So there's 4 that ask you to do this. And here's what hopefully you see here. The first question says, compare when you were hanging 10 grams and 40 grams. So if you take 40 grams and divide it by 10, that is 4 times bigger. Now, if you take the speed of the wave when you were hanging the 40 grams, and if you take the speed of the wave when you were hanging 10 grams, that gives you a ratio of about 2. All right. Now let's keep going and you'll begin to see the pattern. For question number 2, they say compare the 10 with the 90, which obviously 90 grams compared to 10 grams is 9 times bigger. But then if you compare the speed while you're hanging the 90 grams with the speed while you're hanging the 10 grams, you get a factor of 3. Now, it's probably not enough to see the pattern, but I'm going to point it out. Do you see how 2 is the square root of 4? 3 is the square root of 9. And that continues. In question 3, if you compare the 10 grams to the 160, so 160 over 10 is 16. And if you compare the speed when you're hanging the 160 grams to the speed when you're hanging the 10 grams, you get a 4. There it is again. You've increased the tension by a factor of 16, and the speed has increased by a factor of 4. So we're seeing that the speed increases, but not in the same proportion as the tension. In fact, it's obviously increasing as the square roots of it. And the last one we did We're comparing the most weight we hang, which is 250 to the 10, which is a 25 times increase. And as we measure the speed of these two, the speed is increased by a factor of 5. So again, the square root. So that's how we can answer then the question here. It says, what do you conclude about the mathematical relationship between the tension in the string and the speed of the wave? So I would say, if you put it in symbols like this, the speed is proportional to the square root of the tension. Now you could write it in words and just say the speed is proportional to the square root of the tension. And so either it's absolutely fine. Now I'm going to go on to number 2, part 2, just maybe for completeness on the video. I didn't get the impression that's really what you were asking, but maybe I should flip back over to the chat here just to see. You gave me a nice link. I'm going to click on it. What's this link taking me to? Oh, your answers. Oh, nice answer. And of course, they should be my numbers. So it looks like you got a pretty close to a 2 here. You got a 208. That's good. Now this is a little on the low. No, little hair high, but good. 3 times bigger. And 4 points. Must be a 2.
Those from the video. I mean, those data is from video. The level video.
Yeah, thank you. Yeah. So this is the data from you did the calculation. I did the video, I did the measurements, and you did the calculations. And these calculations are excellent. They are right on target. Yeah. So yeah, perfect. See how when you take the ratio of the speeds, you got very close to 2. You got 2.08. And then this is very close to 3, and this is very close to 4, and this is very close to 5. And so the only thing I would say on this link that you gave me is that number 5, this would be a better answer. You just said it moves along more quickly, and that's true. I mean, this is saying more tension, more speed. That is true, but we can do better than that. We can say how the speed, or excuse me, over here, how the speed is related to the tension. So we can say speed is proportional to the square root of the tension. So that's what I would encourage you to change. All your others, the first 4 are great numbers, very close to the numbers that I said. And then the conclusion you want is this. Does that help?
And how about part 2?
Oh, yeah, great. Okay, so part 2. Well, I guess I'll put a line right here, and let me jump back to the questions on part 2. What did I do with that? Okay. So in part 2, it says, compare the 2 average values of the speed in air that you found in part 2. So I'm hoping, and if you want to send me a link again, I can look at your calculations. But when I did the video lab, you should have come up with a speed, which is wavelength times frequency, of about 34,000 and change. let me call it 34,400 centimeters per second, which is the same as 344 meters per second. All right. And we did the two parts, and hopefully both of them are in this area, okay? Because what you're supposed to be noticing here is that the speed of sound is this number that not only did we just measure, but it agrees with what we've been talking about in class, that this is the speed of sound at room temperature, but then also that the two different frequencies, let's see, this would be the first time we did the experiment, we did it around 750 hertz, and then the second time we did it, it was around 1500 hertz. So hopefully you see those two. Let me read the fine print here. It says, keep in mind that these were measured using two different frequencies. That's their point. Does it seem reasonable that the speed of sound in air is the same for all frequencies? So they're trying to get you to see that the speed of sound is not dependent upon its frequency. And so with you, in this case, increased the frequency from 750 up to doubling it, we see that the wavelength went down and the speed still remains the same. And so that's the conclusion they want you to see, that the speed of sound does not depend up on the frequency. And we only tried it with two frequencies, so I wouldn't call it a complete proof, but I would say it was a good indication that had I tried it at a third frequency or a fourth frequency, it's just not gonna change. Now the next question, it says, how did the values of the speed of sound compare to the accepted value? Now the accepted value is this value at room temperature. Now I just wrote down that number, so whatever you calculated, go ahead and see how close that compares, but it's got to be really close to that. So it says, how did the values compare? You can say very close, and then it asks you to actually calculate it. Let's say instead of got 345, I got, or 344, I got 350. So what that would mean is I was 6 off. So I would go 6 out of 344, then multiply by 100%. And this would be my percent error, saying, okay, how close did I get? Now, the last one just says, what's the relationship between the wavelength, the frequency, and the velocity? That was this. So you could just write that and just call it good and say, okay, that's their relationship. And then the last one is to sketch that standing wave. So the standing wave looked something like this. And this is, I think I did this one at the end of the video because it's always the hard one for students, that you draw this, and then a moment later, the wave looks like this, and a moment later, it looks like this, and then a moment later, it looks like this. And that's probably enough. Just probably 4 drawings at different moments in time are pretty good. And then they want you to label things. They want you to label where the nodes are. So these points here that never go up or down are the nodes. So maybe put the word node and point to it. Sketch a standing wave, label the nodes, label the antinodes. So again, maybe I'll put it down here, antinode. The antinode actually does move, a little harder to point to. It's this point there. And then later it's this point, and then this point, and then this point. So maybe a vertical line would be a better way to represent the antinode. The wavelength is when it goes up to a crest and then down to a trough. So we might want to do 2 humps in here. So label that as the wavelength. And the amplitude is how far it goes up from 0. So it's not from all the way the top down to the bottom, but it's from the middle up to the top. And so that's how you would want to draw that picture. Yeah. And so hopefully that helps. I don't know if you wanted to send me the link to what you've done and I can look at what you've done, or maybe you haven't done any yet and that would be the answer that you want to put down there. Does that help?
Yeah.
All right. Good. And I guess I should scroll down. I think that was the end of the questions, right? Yeah, because the next page is the next lab, the air thermometer. All right. Good. All right. So we got a fun 102 one done this morning. All right. So let's see who's next here. I think I saw Scott somewhere before this. Scott. Oh, it just says he'll be right back. Okay. So then Gina. All right. So let's try. And 33.11. So that must be chapter 33. And number 11, can you talk about the last step they do on the first line? I don't follow the substitution. Okay. So if it don't be okay with you, Gina, I know your question was a little more specific about the last line, but since it might be nice just to make the whole video, I'm not sure how much it requires to get to the last line and which is the hardest one, but at the risk of boring you, I'm going to go ahead and write down the time here, 10:26. Go ahead and do the whole thing. So that way it's on video, because I think a lot of people get a lot out of the videos after I send them, and they're on their own time and they can kind of scan through them. All right, so let me find the problem now. Okay, so what do I do with the questions? Here we go. Here's your class. All right, so called up the PDF. Let me scroll down. Oh, I got a long way to scroll. We must be at the end of the semester. Okay, so here is chapter 33 and then number 11. Oh, and it says review problem. I wonder why it says that. Oh, yeah. This is both easy and hard. What I mean by that is it's pretty hard, and then when you see how to do it, it's pretty easy. It's really taking us back to chapter 31 on flux, but let me just read it here. It says, determine the maximum magnetic flux through an inductor that is connected to a standard outlet. Now, they gave you a little hint, but I just want to point out, because I think it's good for you to know, that the standard outlet in North America is a voltage that changes with time. So it's an AC voltage. And we like to write it this way, that there's some maximum. And then it oscillates, and depending on when you call time equals to 0, it can be purely a sine shape, or it could be purely a cosine shape, or it could be some phase in between. The point is, it's just going up and down, sort of like I'm trying to draw in this picture. And usually for our own convenience, we like to call time equals to 0 some point on here so that it looks like a sine or a cosine. Sometimes a minus cosine is useful. Sometimes even a minus sine is useful. But usually some kind of phase like 30 degrees isn't very helpful. So for my case, since I don't really need the phase or anything about it, I'm going to put my time equals to 0 right here. And so if this was my graph of voltage versus time, by putting it here, I am then setting the phi factor equal to 0. And I'm just saying, okay, that's my phase. All right, so really what I have, and they were extra kind, because they told me what the frequency is, 60, and what the maximum voltage is. But I'm going to use this as an opportunity to point out that the review part of this, and I don't think this is the major part of the review. The major part of the review is actually going back to the flux of chapters 30, 31. But this is what I hope you will keep in mind, as you plug in the vacuum cleaner or you plug in your Christmas lights, you're like, okay, this plug is an alternating voltage, peaks up at 170. So at some point it goes down to a negative 170. And it goes back and forth 60 times a second. So that is part of the idea. Okay, so now I can actually do the flux calculation. And now let me just check this question real carefully. Determine the maximum flux through an inductor. So I think we have just an inductor. So if I was hooking up this circuit, this would be the AC. This then here would be the inductor L. And I would, just be directly connecting it to here, okay? Now, here's where the slash review comes in. If I was hooking this up, this is basically saying all the voltage from this power supply, so that means that thing right there, is going to the inductor. And the voltage on the inductor is minus this L di dt. And that's what we learned in chapter 32. So I guess that might be part of his review. But I really think the majority part of his review is really going back to 31, because that voltage is the EMF. So let me write it as script E, and let me write it as Faraday's law. I would write this as minus N, the number of turns in the inductor, times d phi dt. Okay. And so I'm going to take advantage really of this part, because then determine the maximum flux. Oh, wait. I think we got to do a little step here and put these two together. See, these each have derivative of time. So if you integrate them, this says that L times I is equal to N times the flux. And so this right here is the flux. And so the maximum flux, now I'm drawing a blank here, is related to the maximum current, but they don't give us enough information for the maximum current. So I don't think I want to do that. I think I want to jump back over to integrating the voltage. Well, let me try that. And maybe I should turn to your question now a little bit better. Let me write this as 170 times the sine of 2 pi 60t equaling n, and I've got the derivative of phi over t. Well, let me do an integration of both sides of dt. So not worrying about the negative, that's my n times my flux. That's what I want. And so on this side of the equation, I get the 170 let's see. So the integral of sine must be a cosine. Let me just, or is it a minus cosine? Yeah, it must be a minus cosine. Although I have a minus here. And either way, I'm going to ignore the minuses. Okay. Let's see. Minus cosine would be 0, 1. Okay. And then, of course, let me not forget the chain rule. So this is 2 pi over 60. Let me just double check by taking the derivative. I take derivative of the minus cosine. So 0, 1. Okay. And then divide. Yeah. Yeah. So that looks good. So anyways, the maximum then would be that number right there, because this is a cosine function that goes up and down. This is the flux, and so I'm looking at 170 over 2 pi 60, I believe. I better check the answer on this one for you, Gina. Let's see. 33. Number 11. What did they do? And they do... Oh, now they write it in kind of a weird way, but I think we're looking at the same number. Let me check here. I like my approach a little better here. So the maximum, if it's 170, divide by 2, divide by pi, divide by 60. And so this would be 0.451. Does that agree with them? Yeah. And it would be a flux, so it would be Webers. Yay! Now, if you're curious, since your question, Gino, was really about what they did, maybe I will kind of look at what they did. Not real excited about the way they did it. I think this was a little more straightforward. But what they did is they did this. I jumped back to the voltage and integrated it. But they left it right here and said, okay, the inductance times the current is equal to the number of turns in the inductor times the flux through one of them. Then they said that, well, the maximum then is going to occur when you have maximum current. Then he says, well, you get your maximum current when you take the maximum voltage and divide it by the reactance of the inductor. Now, the reactance of an inductor is omega L. So the L's cancel off, and then you get your maximum voltage divided by omega. And that's exactly what I have here. I have my maximum voltage divided by the omega. Maybe I should have left it in symbols, but if I left it in symbols, that would have been maximum voltage. That would have been the omega. Now he does something kind of weird. Let me go back to the question. I'm not sure why this is here. Didn't they give me? Oh, I see. Okay. My apologies. I said the author helped us out by telling us the maximum. That's not quite true. The author helped us out by telling us what the RMS is. Okay. So the maximum is the square root of 2 times the RMS. So if you take the square root of 2 and multiply what he gave us, 120, you get the 170. So I just put the 170. I apologize for that. I thought I had read he was giving us the maximum. He given us the RMS. Okay, so I should have included this step before I got the 170. So I could either use his hint or remembered it was 170, which now makes sense why the author of the solution said, okay, to get this, you have to take the square root of 2 and multiply it by the RMS to get the maximum, and then divide it by omega. And then he even simplifies some things. He takes the square root of 2, he takes this maximum, then he puts the omega, which is 2 pi f. And then he does one more step, and he goes, well, we could cancel a square root of 2 here, leaving me with the square root of 2 times pi times f. And so then we can put in the 120 and the square root of 2 and the pi and the 60. So presumably that comes out to be the same thing. 120 divided by the square root of 2 divided by 60 divided by pi. Yeah, and sure enough, same. So now I totally see why you're asking what the heck the author did and why he did it the last question. So I should now that I've done it, I kind of like that. Your author used the idea of reactance and current in order to get the flux, whereas I just went back to Faraday's law and integrated it. And so then actually, I take it back. This is kind of a neat way of doing it. This is actually doing it with circuits instead of just the fundamental physics with Faraday's law. Yeah, but what the?
Okay. Would you be able to go over steps, step by step, and explain what you, mainly the integration?
Oh, okay. So okay. Yeah. Okay. So I'll leave the author ones here. I think you're asking about mine, right? The integration here?
Right. Also, there's some little bit of lag. Yeah.
Oh. Is there
It's
still
not
lag?
too bad.
Yeah. One. Okay, I'm going to write the number 1 and say it at the same time. 1, 2, 3. I think it's okay. You might have lag on your end. I understand that. I can't help
Okay.
that.
It's not too bad.
Okay, good. Okay, so maybe so let me come back for some clarification here, and let me in my method. I'm just going to go all the way back to Faraday's law again. So this says the EMF is equal to the negative, technically, the number of turns times the derivative of the flux, the time derivative of the flux. Now, I personally think the hardest part of this problem might actually be find the maximum flux. Because what then am I looking for? What am I trying to solve for? And that would tell me I want to solve for not just this symbol, which is the flux, but then the flux as it goes through every single loop. So this is the flux going through one loop and then multiplying it by the number of loops. Okay. So that's really the question here. And to me, might actually be the hardest part of this question. How do I take those words and what symbol am I looking for? Okay, now, if you look at Faraday's law, you will see that we don't quite have this, but we're really close. This is the derivative of that. So if I were to undo a derivative, that's called an integral, I would get it. So I would say if I integral the voltage, so on this side, if I integrate what's happening on the right-hand side here is I am really undoing a derivative. This says the derivative of the flux. This says take the integral of the derivative. they undo each other. It'd be like asking somebody to take a number like 5 and, hey, why don't you take the square root of 5 and then square that? What do you get? They're inverse operators, and so they undo each other. And so you're going to get that. And so I think part of your question was, why am I integrating the voltage? And this is why. To the other side of Faraday's law, I want to get the flux, not the derivative of the flux, but I want to get the flux. So I have to do the integral. So that means on the other side of the equation, I've got to integrate the voltage. And the voltage, since it's plugged into a common outlet, and I should say common outlet in North America, I've got to write this as 170. I think maybe I'll just use symbols. V maximum times the sine of omega t. And so doing the math here, I would just pull out V max, and then I would have to integrate a sine function. And the integral of a sine function is a negative cosine function over omega. I always like to check it by taking the derivative and see if I get a sine. So I like to draw a negative cosine, and in my mind take a derivative of that. So a derivative is a slope, so I get 0, 1, 0, right? So that's a sine function. Good. So the negative cosine, the derivative of that is the sine. Now, of course, the derivative of a chain rule would give me the omega, which is why that omega is down there, so it would cancel because there's no omega here. So good, taking the derivative of that does give me back to that. Good. And of course, this is what we're looking for, the n. So this would say this is the flux really as a function of time. And so the last part of that, it would be what would be the maximum. And since a cosine function goes up and down between +1 and -1 as it goes up and down, then the stuff here would be the maximum. So V max divided by omega is the answer. And that's what I have in this calculation. V max is 170, and divided by omega, which is 2 pi 60, gives me the 0.451 Webers.
Okay, that makes a lot more sense. For some reason, I was thinking it was set equal to I, and that was thrown, but now I see it's equal to.
Oh. Yeah, that symbol phi, capital Greek letter phi for flux, and capital I aren't too far apart, and they can mess things up. Sometimes a lowercase l and an I getting all messed up too. All right, well, good. Hope those were helpful. And I will move on. Speakers out of the way. Okay, nice. And let's move on to the next one. I think it was Daniel here. Okay. Do you have a PDF of chapter 34, homework and solutions? I don't. In the past, what I've done is, and I'm going to do the same thing here on Sunday, as we get to the last 2 weeks and we get into this chapter 34, I'll make a comment on what sections, and I'll even refer to the problems. I'll take it one step further since you're asking. But I just say, okay, why don't you look at this section, this section, this section, and then you can just go to the PDF of the textbook and do the ones in the textbook. But okay. I can, so I've never made a PDF because you have a PDF of the textbook. So that's why I've never bothered.
Do you have a PDF of the solutions or no?
Oh, And so, yeah, and then so the second part of your question, let me check. So are the solutions for 34 not on here? Let me check.
I do not believe so.
Oh, it says not found. Okay. I was not aware of that. So we must somewhere. And it's not loaded on here. Okay. So note to me that I need to find those somewhere. And they, huh. I doubt seriously if I have those old things on my Google Drive, but they've got to be somewhere in my office, some DVD somewhere. Yeah, I'll hunt those down. And I actually, hopefully I won't forget on Tuesday. Let me even just give myself a note. Hunt for solutions to 34, because I don't want to forget, because what I'm planning on doing tomorrow is to kind of look at my video lectures for 34. I remember doing those video lectures, and we didn't have much time for 34. And in a face-to-face setting, I go, well, this is the best we can do. And if we were face-to-face now, I might say that. But now I have the potential of making a new chapter, a lecture for chapter 34. So that's what I'm thinking on Tuesday for my schedule, is to go in and do a lecture for 34 and give you guys a little more completeness to chapter 34. I want to balance that with also your time. It would be nice to have a full, complete chapter 34 lectured and done. But in some sense, I don't know if that's fair to you guys, because in a normal setting, I wouldn't have done that extra work. And I don't want to say, well, just because we are online, we can take more time than we would have in class. I don't think that's really fair to you guys. But so I want to maybe make a balance of that. Maybe I'll make a more complete lecture, maybe not 100% complete, but more complete, but yet keep the assignment kind of on the small side and the test on the small side. So I don't really know what I'm going to do with 34. But anyways, that's a long way of saying that I plan to go in on Tuesday and do instead of a lab, do a lecture on 34, make it a little nicer than what we have. Although I say that, I haven't looked at it. I'm going to go look and see what that last lecture on 34, see how complete it is, and realize that that's what we've normally done. And
Well,
all that good.
Maybe what you could do, because you could make that last lecture and then keep the work the same, and then say, hey, if you guys are interested before you go into 123 or after the semester's over, go watch that last lecture, because I had a math teacher that did the exact same thing. He it was like a section that we don't really need, but he's like, if you guys become tutors for 200, you guys should go watch that material and learn that material. And so
yeah, okay, yeah, that's a good idea. So yeah, I really don't want to give you any extra assignment. Yeah, and I like that approach. So I'm leaning that way. But all of that was to point out that I really want to find those solutions and get them posted there. I don't know why they're not. And anyways, if I'm there on Tuesday, I'll rummage through my DVDs and find the old PDF solutions to this. Yeah. Okay. Good. All right. So that was the next little question here. All right. Let's see. Then we got
I think the next question was me as well, but Gina just told me that number 30 was actually on last week's Friday, so I can just go back and look at that.
Oh. Okay. Okay. Well, then.
So that way
right.
we can get some questions that haven't been asked yet, maybe.
Yeah, but looks like we're at the end here. There are no questions in the chat room.
Oh, I mean,
Oh.
if no one
It looks
has
like
any
Dana
questions.
popped in. I don't know if Dana wanted to throw a question up in the chat or
Yeah,
ask me.
well, I'm kind of looking through my homework. I had questions when I was going over chapter 17 last night, but now that I'm
Oh.
rereading them, I think I was doing the wrong, like I've got problems on here that aren't on the homework. So I'm trying to find out where I was reading and which ones I have a problem with. So
Okay.
I'll ask once I figure out what my questions are.
Okay. Nope, no problem. We'll be here.
Thanks.
Let's see. And, I am kind of curious. Your chapter 32, number 30. What was that one? Well, I'll like I said, I'll let you look that one up. Oh, 2 coils side by side. Yeah. Yeah, and actually, if I remember right, that was the first recording. That's one Gina did. Yeah, I asked about last week.
Yeah, and I just saw that it was on last week, so I can look that up later. Then,
Good.
like the other question I had, you sent a video on last night, so I'm like, okay, cool. It was question 18 for 32, but you sent a video on that last night, so I'm like, okay.
Good. Yeah, a couple people had asked about that one, and it was getting to that time. I said, you know what, someone will probably ask that tomorrow, but nah, I'll just make one. And I made it. It actually turned out to be harder than I thought. It was a longer problem, and I was pushing a meeting time. I don't know if you got a chance to see the video, but I learned
Yeah,
something
I was
new.
gonna
I
look
had
at
my
it.
camera up here, and my alarm went off. You know, that was my alarm was to make sure I didn't miss my meeting. And then the camera, it shut off my record. I was like, wait. So I started recording it. I thought, I'll just finish it up. And then it took even longer than I anticipated. And my final alarm went off and then stopped it again. And right as I was at the end, which wasn't a big deal. But then I go, well, should I just post it as part 1, part 2, and part 3? That would be easiest thing to do. Or should I put it in a video editor and put it all together? And I go, well, we'll make it nice and do that. And then I ran into all kinds of troubles because I first tried to email them to myself on my phone, and it said, no, too big. And I go, oh, okay, I'll just put it in my Google Drive and then put it on my computer. So I did that. Then my video editor said that the format that it's in is a format that this video editor doesn't recognize, but for $5 you can buy an extension and get it. And I, oh, okay. So do I go, no, I'm not going to do that.
Oh,
Do you have a
Professor?
Mac or Windows based? Sorry, Gina.
Well, yeah, my computer is Windows based, but my phone is an iPhone, and that's what the extension was. And I was like, oh, bummer. What I ultimately ended up doing then is I go, I probably should have just upgraded for $5, and because I'm probably going to run into this trouble again. But I go, I know what I'll do. The iPhone, I've noticed when my iPhone, like these that we're recording today, when I upload those to YouTube and then download it onto my desktop, it automatically changes that all to an MP4. And so I know YouTube has their kind of own format. Or maybe they've gone to MP4 now. I'm not sure. But so whatever format is in my phone knows when I go to YouTube, it converts it. So it did that. So I actually uploaded it on YouTube, the 3 parts, then downloaded it from YouTube, put it in my editor, spliced it into one, and then put it back on YouTube. And I was like, okay, I'm making this thing harder than it needs to be. all because the alarm went off in the middle.
Professor, can I ask anything about transformers?
Oh, sure, absolutely. Yeah.
Just how do I identify the end primary and secondary?
Well, when you have a real transformer and you're playing with it, they are literally, I'll just draw a picture here. They literally are, on one side is just a wire wrapped around. And the other side is literally just a second wire wrapped around. And to make sure that the flux from one of them gets into the other, maybe I'll do a different color here. You put some material like soft iron that will help direct the flux. They even work better when you literally just wrap the second one around the first one. I didn't want to draw it that way because it gets kind of messy. But what I would say then is there is no set, one side is the primary and the other side is the secondary. There's none of that. When you pick it up, you can make either side a primary or either side a secondary. And so what determines the primary is usually your thinking, your terminology. When you say, okay, what I'm going to do is I'm going to plug this into the wall and I'm going to use it to run a light bulb or a computer or whatever you're trying to run. So we often then say that the primary side, so I'll put P on primary, is the side where you're really getting your main power that then feeds to what you're trying to run. And so that's your secondary. But if I had, say, N equal 100 turns here, and so I'll call it N primary and then secondary, this 2-to-1 ratio would say that the voltage coming out of here is twice the voltage I put into it. But if I literally just switch it around and say, hey, you know what? I want to do it different. I want to, instead of run my lights here, I want to plug this side in. And then over here, I want to run my light. Well, then all of a sudden you would start saying, well, I have 200 turns in my primary and only 100 turns in my secondary. So you would change this from primary to secondary, and then you would say this is a step down transformer. You would say it lowers the voltage by a factor of 2 instead of the other way, raising the voltage by a factor of 2.
Okay.
So
I'll just carefully the language in the problem.
Yeah. So when it comes to a problem, that probably doesn't really help you. What really helps you is you've got to take a look at, I guess maybe the better way to say it is maybe not call it primary and secondary, but call it 1 and 2. Because they're going to give you the voltage at either 1 or 2, and you got to find it at the other one. And so maybe write this as, voltage at number 2 is equal to the number of turns in number 2 over number 1 times the voltage in number 1. Maybe it would look better with a symmetry design.
Like number 40 says it has a 13-to-1 ratio and it's used with the 20-volt device. I wasn't sure if volts every.
Yeah, say that again. Okay, so 41.
40,
Yeah, so
it gives you a ratio 13-to-1, and it says it's used with the 120 device.
So where is this? What number is this?
Number 40.
40, 40, 40, 80. Oh, okay. So now read the first part though. I'm going to read the whole thing, but the first part, notice it says a step down. So it says a step down transformer is used for recharging a battery of a portable device on a tape player. The ratio of the turns is 13:1, and the transformer is used with, the standard North America household service of 120 RMS. So what that would tell me is the input, what you would call the primary, is 120. I know that because what I'm going to do is plug it in. That's where I get my energy source. And then I would know to divide that by 13, not multiply. It's not a step up, it's a step down. And so the number of turns would either step it up by 13 or step it down by 13, depending on which way you run it. But they make it very clear in that first sentence, it is a step down transformer.
Oh, so 120 is the wall? So that would
Yes,
generally be the
yes.
primary in most cases?
Because because you're gonna plug it into the wall and get get your energy from the wall. So that's your primary. Yeah, and
Okay.
so yes, my first calculation here would be the transformer used in household homes. In this particular ideal transformer, it draws 0.35 amps from the house. What is the voltage? So there's the voltage, and that would be RMS voltage because I put 120 for RMS. And so there's the answer to A for number 40. And as long as you're asking, I'll continue on here. It says, the current supplied to the tape player from the transformer. Now, the general idea of a transformer is that the power going in equals the power going out. Now, that's in a perfect world, which I think later on you have a problem. I remember reading it somewhere that there's a problem where it says transformers aren't perfect. They, will transfer like 95% of the power. But for this problem, they say an ideal. So they say if this particular ideal transformer draws it, and here's what I'm getting at then, the power is the currents measured in RMS times the voltage measured in RMS, and the power out is equal to the currents in RMS times the voltage in RMS. So if the voltage in the primary is 120, and of course it's reduced by a factor of 13, which is this 9.23, but I'm going to write it as 20 divided by 13. That means that the current over here in the secondary must be increased by a factor of 13 compared to the primary, because the two have to be equal. So if this number decreases by a factor of 13, this number must increase by a factor of 13. Now, which did they give me? They gave me, in a particular ideal transformer, draws 0.35 amps from the outlet. So they're giving me this number. So that means the currents over here in the secondary would be 0.35 multiplied by 13. And so a step down transformer can get, the name step down can get a little confusing because we step down the voltage by a factor of 13, but in the process have stepped up the currents by a factor of 13. So this is the number they're looking at. So 0.35 times 13, mean we're looking at 4.55 amps in the secondary going together with the 0.93 volts in the secondary. And so these two multiplied together is the same power being delivered in the secondary and then charging this battery of this portable player. And it came from the power out of the wall, which I think then is the answer to part C. Oh, and I should say, so this is the answer to part B. What is the current supplied? And then C, how much power is delivered? And so 4.55 times 9.23 is about 42 watts. And of course, since the power coming out of the transformer is the same as what goes in, conservation of energy, I could have just as easily done the calculation by saying it's 0.35 times the 120 and also got 42 watts. So there's the answer to C.
All right,
Yeah.
that makes enough sense, I guess.
Yeah. And I'll just check. Let's see, 42, 5.54, and 3.23. Right, good. Yeah, so anyways, it sounded like your question wasn't so much about the calculations, although since this could be helpful, I thought I'd put it all on video there, but also deciding which one is the primary or the secondary, agreed, can be confusing because there is no set way of doing it. But maybe the short answer, as you said, is if you're plugging something in, then clearly the energy source is coming from the plug and it is going towards whatever you're plugging in. And in this case, a portable audio player that we're trying to charge up the battery, which batteries tend to be low voltages. So that's why you would want a step down transformer. But the other reason we know to do the numbers the way I did is they made it very clear that it's a step down. And so well, I guess you have to recognize it's the wall. And so you're taking the 120 at the wall and you're stepping it down to some lower voltage. In this case, around 9 volts. Doesn't surprise me because that's probably the voltage that it runs off of. Be very common to run 9 volts. And of course, the other advantage is you increase the
step down means that N2 is less than N1.
Yeah, mathematically,
Okay.
yeah.
Okay.
Yeah.
I think
Yeah,
I'm gonna
so-
keep working problems and
Okay.
come back a little bit later, maybe.
Okay.
Thanks for your help.
You bet. Sure. Nice. All right. Well, let me check the chat room. Oh, okay. Nothing new. Okay.
If Dana doesn't have a question, I have a question about 44 part B. I just don't know where that formula for resistance came from.
Okay. 44B, you say. And then is that at
Chapter 32.
32? Okay, that's what I wanted to check here. Okay, so something like that is. So chapter 32, 44 And you're really asking about B. Let me switch over to the questions. And I think I need to scroll up because I think I was just in 33. Yeah, okay. So 32. Oh, 44B. That's on that page that I sent out separate. Okay, because I got stuck together. Yeah, 44B. Actually, I'll put it in the video camera here. I printed a hard copy of it. So 44B, it says an active figure, 15. Let R equal this, let L equal this, let C equal this. Calculate the frequency of the dampening oscillation, and then what is the critical resistance. All right, you didn't ask about A, so I won't spend too much time here on A, but I will say that when you're working with this LRC circuit here, or RLC circuit, and I should double check. Is that really the circuit? They say look at figure 15. Give me a second to jump to the textbook, but I think it was because I assumed it was because they listed all of them. They listed an L, an R, and a C. But I'm going to go to chapter 32 and look at figure 15. So that's figure 16. I got to be close. Oh, okay. Yeah. So figure 15 looks something like this. They've got a power supply with a switch, which they show in the closed position, coming over to a capacitor so they can charge the capacitor first. Then once the capacitor gets charged and you disconnect the switch, you would swing it over here to the inductor. And so you would have a charged capacitor, and then you would have your R, L, and C all in series as it would oscillate. So if I were to plot, say, the voltage on the capacitor, it would do this. And they went through the detailed math on this. They said that the dampening frequency would be the square root of, and they have the 1 over LC minus, and this I might need to scroll through the book. This has an R over 2L, I believe, and a square.
Yeah, that's right.
Is that okay? Good. All right. So, and again, you don't want this one, so I won't plug in the numbers, but that's what A is for anybody who sees the video later. Just plug in those numbers to get the dampening frequency. But you're off to B, and B uses an interesting phrase. It says, "What is the critical?" Now watch this for a moment. If you had, say, a small resistance or almost no resistance here in this equation, if you ignored this, then you would just get this standard square root 1 over LC, what we call the resonance frequency. It would just keep going back and forth at that frequency. So what this equation is really saying, if you take a moment to read the math, is that without a resistor, there is a natural frequency that this thing will oscillate at. And it will just keep going forever and ever. When you throw in a resistor, so you throw in the R, notice there's a minus sign. What that says is you would get a little smaller frequency. So if I change the color and said, all right, if I throw in an R, let's say a bigger R, it would look like, and I'm trying to draw in green, it would be a lower frequency. Of course, it'd be more resistant, so it probably wouldn't go up and down very many times, but it would be a lower frequency, or in this case, a longer period. Let me do another color on here. See if the purple stands out. But as this resistance keeps increasing, this frequency eventually goes to 0. There is no frequency. Because if you remember, the full solution to the voltage looks something like this. It said the voltage is, and it would be the initial voltage, and then it would be this decaying exponential, and then this cosine. And so what they're really saying here is, how much would you have to increase R in order for this term to essentially go away? That is cosine of 0, which is equal to 1. And so they're trying to get you to realize that at some point, the resistance can become so much that you don't get any more oscillations. And so to say an LC circuit oscillates, or LCR circuit oscillates, is a little misleading, because it really depends on how much resistance you have. And so when you get to that magical number where the resistance is so great that you don't get any oscillations, we call that the critical resistance. So that's that word there. What is the critical resistance? At what resistance is it so high that you don't get any more oscillations? So they're really saying, when does omega equal 0? That's the key to the problem. So
Okay.
then if you square both sides and move it over, you would get 1 over LC, and over here you would get R over 2L to the square root.
Could you move your paper up slightly? It kind of has that
Oh.
like slow-mo. Yeah.
Yeah,
Awesome.
yeah, sorry. Yeah.
Okay. So
So I'm going to set the frequency to 0 as the magical
okay.
step.
Okay, cool.
Yeah. And then, actually, I was going to go to another page, but maybe I can just finish it on here, because first I would take the square root of 1 over LC. Then I would multiply by 2L. So then if I grab the numbers they gave me, 2 times L, where is L, 44? They give me 2.2 times 10 to the negative 3. Then I'll go times, and then I got the square root of 1 divided by the product of L. So L is 2.2 times 10 to the negative 3. And C is 1.8 times 10 to the negative 6. And looks like roughly 70 hertz. Oh, and looks like my phone disconnected for some reason here. Let me go back to my phone. Camera here, and while that's reconnecting, why don't I jump to the answers here? Let's see, that's chapter 33. Let's go back to 32. And this was 44, right? Scroll down. 44, yeah, critical resistance, 69. Well, I rounded it. 69.9 is what they left it at. So good. Oh, let me finish connecting the phone. Ah, there we go. All right. So I think the camera went off right here in my calculation. This R and the 2L. So I was typing things on my calculator here when I think it went out. At least when I noticed it went out. And then this is the 70, 70. Oh, why did I put hertz? 70 ohms. Yeah. So 70 ohms would give you the critical resistance that would give you 0 frequency.
Okay. That makes sense. Awesome. Thank you.
Mm-hmm. Set up my next page here. How are we doing? Oh, actually, time's working out really well. Looks like we're getting towards the end of this session. See if any of you guys throw anything back into the chat. Ah, yes, Dana. Okay, good. I have a question about the standing wave lab. I bet you do. Most do. Don't feel bad. The relationship between the frequency. Oh, okay.
Those questions are hard for me when it says like, what is the relationship? I always like, I can never figure out what I'm supposed to say.
Okay, actually, you didn't ask this, but I'm going to backtrack. Because the question I usually get is the harder one. That was the first 5 questions. So did you catch this? Did you catch that in question 1, you were comparing the speed at 40 grams to 10 grams, which is a factor of 4. And the ratio of the speeds went up by a factor of 2.
Mm-hmm.
Okay. Now, in question number 2, you were to compare the 90 to the 10, which is an increase of a factor of 9, and the ratio of the speeds is about a 3. And so a pattern's beginning to develop that it's always the square roots.
Oh, you said that in the video, but I didn't make the connection.
Yeah, right. And very few do. I don't, yeah, I guess it's just because this is harder. But the first 4 questions is, and I know this isn't your
That's okay.
question. I will get to your question, I promise. But I just wanted to go back here because this seems to be a hard one for people, and rightfully so. So the first 4 questions, you hopefully did something like this, that you saw the tension increase by a factor of 4, speed increased by a factor of 2. Then in number 2, tension increased by a factor of 9, speed increased by a factor of 3. In question 3, tension increased by a factor of 16, and the speed increased by a factor of 4. And then finally, in the 4th question, the tension increased by a factor of 25, and the speed increased by a factor of 5. So the answer of number 5 is to say something like this, that the speed is proportional to, and here's the key part, the square roots.
Is this a 102 question?
Of the tension. Yes, Daniel, this is a 102 question. Yeah.
Okay, I'm gonna take a break. I'll see you in an hour.
All right. Yeah, I'll see you 12:30. Okay.
All right, bye.
Yeah, our time's about up. I'm gonna take a little break. Okay, Dana. So you could put it also in equation form. You could say something like this: V for velocity, and then this little Greek letter alpha for proportional, and then square root of t. So feel free to write it any way you want.
Okay.
Okay.
Yeah.
But I also wanted to then not only review these 5, because and it sounds like I'm glad I did, because those 5 can be a little challenging.
Yeah.
But also, this might help you on part 2, because part 2, and let me just jump to your lab manual here. I got it somewhere nearby, close. Ah, here it is. Part 2, you specifically asked I think it's the second to last question, which says, what is the relationship between them? Okay. So let's see. This would be 5, 6, 7, 8. The second to last one would be question 8. You could do this, and this might be helpful to you because you said you didn't know really how to word it. You could just say, this is the relationship between them. You take the wavelength, you take the frequency, you multiply them together, you get the velocity.
Okay.
You could put it in words and say, speed is the product of wavelength and frequency. So feel free to put it in words, but I am just as happy with and convinced that if you put it in equation form or word form, you're understanding the relationship between them.
Okay. Yeah. I don't know. I am having a difficult time with this. It's been a long time since I've been in school, and I just like, I used to be so smart. The first time I was in classes was like 20 years ago, and I was so smart. My brain worked so fast, and I could just like read stuff and remember it. And now I'm like struggling just to understand what the heck the question once,
Yeah, don't beat yourself up too badly. Number one, that is normal for returning students, especially after a 20-year gap. But it also, I think, is something about this discipline too. So comparing, maybe this discipline to maybe another discipline that you did 20 years ago may not be a fair comparison either.
Yeah.
But
Yeah, I was just in, yeah, anyway.
And that's what 102 does really well. I don't know what your long-term plans are, but if you're going into 121, one of the best things you can just really get out of this 102 class is learning that thinking process like a scientist and an engineer in the physical sciences, because it is so different.
Yeah. And that's what I want. I want to do something in STEM, and I don't even know what it is. Right now I'm doing computer science. Like, I'm just gonna like do a computer science for a transfer degree, but like I'm just coming back, so I might change my mind or find something I really like. But I don't even care. I just want to do something in science and something that'll be pleasant and that I'll enjoy. So I don't know.
Well, good. Yeah, no, good for you, boy. I enjoy teaching STEM to students who want to learn STEM because it's so enjoyable. And of course, part of that, as you just said, you got to enjoy doing it. But those people who do enjoy doing STEM, like yourself and, well, really all my students in here, have got such an advantage in this world because it's this type of skill that the good jobs and the mini jobs revolve around.
Yeah.
And so to have the opportunity to have a good job, many opportunities at different jobs. I mean, you could almost go to anywhere in the country and, hey, I want to live in, pick a city and you can find a job there. It's a well-paying job. So you're, not barely making it by.
Yeah.
Usually a lot of benefits, and throw in the fact that you enjoy doing it. Oh, it's awesome. So whether it's computers or engineering or whatever the STEM field is, chemistry or solid state design, all of these are just awesome. And so,
I'm really excited about the all of the, not lectures, but what do you call it when all the teachers get together, like the one you guys just did about like all the teachers came in and talked about their backgrounds and how they got to where they are. That was
Oh,
yeah.
Good. You enjoyed that. Yeah, that was put on by the one of the clubs. It was the
Yeah.
Society of an Industrial and Applied Mathematics. And
Yep.
yeah, that was really good. Yeah. And clubs will do that. They, now you talked about computers. I know the computer club does a number of things.
Yeah.
Now in this whole COVID pandemic world we live in, it's harder for clubs to have activities, but
I'm really enjoying it because yeah, I was having a difficult time finding a job, and then the pandemic happened, and I was just like, well, I'm going to be homeless, so I have